Wait a second. Okay, let us start some things that we left. Yes, we left on the concentration terms. Okay, now today we will learn about solubility. Today we will learn about solubility. Today we will learn about solubility. Okay, now I guess my camera is detectable. Yes. Now solubility, in solubility, what do we have? We will compare and we will look how solids dissolve in liquids, how gases dissolves in liquid when we add. These are solutes. Okay, these are solutes, and our solvent will be always liquid. We are only learning the liquid solutions. Liquid solutions. Okay, so now at last we will have liquid solutions. Liquid is dissolved to liquid. Okay. Now, first of all, if we dissolve solid to liquid, if we dissolve solid in liquids, can you give me an example, Sanya, when you dissolve solid in liquid? Yes, Sanya.
Glucose dissolved in water.
I didn't get the solute's name. What dissolved in what? What dissolved in water?
Glucose.
Glucose. Okay, solubility of solid in liquids. In liquids. Okay. Now you said glucose in
Water.
water. H2.
Water.
Okay, fine. Now I'm keeping the water constant. Can Ahmed give me another example?
Yes,
You can
sir.
change. You can change the solute and give me an example.
Salt water, salt
Salt.
solubility.
Salt in water. Okay. Salt in H2O. Okay. Now you have given me very nice examples. I mean, if I would have taught without asking you, I would have taught these two solutions only. Now let me ask you. Okay, Fatima, you will tell me, if we dissolve glucose in water, okay, and we dissolve salt in water, is there any difference? Like, do you think if I take a spoon of glucose and just put it in the water, I'm not stirring it now. Okay, now will it easily dissolve, or will the salt dissolve easily when I put a spoon of salt and do not stir it? Fatima, to
Sir,
me the
I
question is,
think salt will dissolve more easily.
salt will dissolve easily.
Mm,
Yes, salt will dissolve easily, right? Salt will
yeah.
dissolve easily. Correct. So that means there is solvent is the same. So there is some fundamental difference between the glucose molecules and the salt molecules, which determines which is getting easily dissolved and which is not dissolving very easily, which needs some kind of stirring when we want to dissolve it. So let us look at how the dissolutions happen, and basically, for example, if I cut papers in pieces and I want to dissolve it in water, it won't dissolve, right? And similarly, if you take some chalk powder and dissolve it, it will not dissolve properly. It will have some turbidity in it. Okay. So what is the reason why some things dissolve? Some things dissolves very nicely. Some things dissolve with some stirring, and when we heat it for a while, then it dissolves more easily.
It's a bond between them.
Bond between them. Okay. What do you? What are other things? What do other people think about the dissolution? Sonia, what
The
do you see?
force of attraction may differ.
Force of attraction may differ. Okay. What about Fatima?
Sir, I said that.
use my, oh, sorry, I'm really sorry. Okay. What about Amalia? What do you think, Amalia?
Intermolecular spaces.
They are molecular species. Okay.
Spaces.
Spaces. Okay, you are saying spaces. Okay. Mariam, what do you
Yes,
think?
sir.
What do you think? Why do some things dissolve and some things don't dissolve?
Because of the size.
Size. Okay, you have given different answers. Okay. Does water dissolve in water? I mean, water is obviously, if you have some water and you put some you put water again, it is
Yes,
easily
sir.
dissolvable, right?
Yes,
Yes.
sir.
Yes, sir.
Okay. That means what is happening here is we have water molecules in which there is oxygen and we have bonds, hydrogens here. We have now let us NaCl. NaCl. Sodium is bonded to chloride. And this bond, what this bond is, plus and minus, this is electrostatic bond, that is ionic bond. Now, similarity between molecule and CL that this molecule has an electron density around oxygen atom
So
and
you
it has lower electron density around hydrogen atom. My voice is correcting.
yes, sir.
Yes, sir.
Still, it would be fine now,
Okay, sir.
right? It would
Now
be
it's
fine
fine,
now.
sir.
Yeah.
Okay. Now is it fine?
Yes,
Yes, sir.
sir.
Now we have a dipole moment. We have a dipole moment. How does this dipole moment arises? This hydrogen has delta positive charges here. This has delta positive. And similarly, oxygen will have two delta negatives. Okay. It has to balance the positive and negative. Now, water is what? Water is a neutral molecules. Hence, H has delta positive. This has H has delta positive, slightly positive charge. And this oxygen will have delta negative. Now, it will have a dipole moment, that is charge separation, and there is a charge separation, opposite charge separation. Similarly, in NaCl also we have plus and negative, plus and minus. So there will be a charge separation and it will have dipole moment. So the mu net is not equal to 0. Similarly, here also mu net, you can say, is greater than 0. Okay. Now, mu net here is also not equal to 0, and here mu net is greater than 0. Okay, greater than 0. So the similarity between these two molecules is that this is also polar molecule, this is also polar, and this is also polar molecule. Okay, these two are polar molecules. Hence, the intermolecular force of attraction, intermolecular forces of attraction, is similar in NaCl and H2O. Okay. Now I am writing NaCl and in bracket I am writing here solute. And what is H2O?
Solvent.
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 Right. So intermolecular forces of attraction is similar in solute and solvent. Hence they dissolve. Hence they dissolve. Now, when something dissolves, we cannot separate out. When we see a water, an aqueous solution of salts, water solution, then we cannot differentiate between where the H2O is present and where is salt present. That means it becomes, we cannot see that with our naked eyes. So this is only because the kind of attractive forces which is in hydrogen, in H2O, which is in H2O, what is the attractive force in H2O? It is hydrogen bonding. It is hydrogen bonding. And what is hydrogen bonding? Hydrogen bonding is nothing but a very high dipole force of interaction, but that is very high dipole force of attraction. So H2O molecules, if I just look at H2O molecules, these are bonded like this. In water, these are bonded like this. We have oxygen and hydrogen. Then these hydrogens are again This have a hydrogen bonding with some oxygen atom. This has hydrogen bonding with some other oxygen atom. Okay. Now this has some with some other oxygen atom. Okay. And so on and so on. Okay. And so on. Similarly, NaCl also has, this is only what, this is electrostatic force of attraction here between the molecules, Similarly, our NaCl also has similar kind of attraction, that is between Na plus and minus. So these are arranged very, there will be again Na will be here also, Cl. So you see how these positive charge sodium atoms are surrounding this negative charge chlorine atoms, right? So same type of electrostatic force of attraction in NaCl also, and similar electrostatic force of attraction between two H2O molecules. Hence, when we have similar intermolecular force of attraction, then the solute is dissolved in solvent, and hence come the thumb rule for solubility. Like dissolves like dissolves like. Okay, like dissolves like. This is very important. Like dissolves like. Okay, so you can start writing from here. You just solid and liquids. Okay, then you can draw this structure, this whole structure. You can draw this whole structure, and then you can write these 2 points. Okay, so if I write the heading here only, it would be easier for you to type out solubility of solids in liquid. Solubility of solids in liquid. Let me know when you are done.
Sir, done.
Done. What about others? Amalia, Fatima, Mariam,
Sir,
Sania?
1 minute.
1 minute. Okay, 1 minute.
Done.
Done. Done.
Yes, sir.
Okay. What about others? Anyone left? No.
No, sir.
Now, so the difference between salt and glucose was that the intermolecular force of attraction in glucose was what? It was covalent and van der Waals forces of attraction in glucose. Okay, if you have C6H12O6, the two molecules of C6H12O6 is not arranged and it is not connected via electrostatic force of attraction like NaCl. Correct? That is why what happens, that is why it is not dissolved as properly as water molecules. Okay. Now, next thing is that if you dissolve sugar, you must know about this thing which is called Shira, right? It is highly concentrated, Like when we make jalebis and all, then we have to make Shira, right? And how it is made? Can somebody tell me how it is made?
Water and sugar.
Sugar and water.
Water plus sugar. Okay, but so just water and sugar, nothing else?
So boil.
Then
Burning.
yes, plus what? Plus heat. So what is the consequence when we heat it? What is the consequence? More sugar is dissolved, right?
Yes, sir.
That means now there is another thing which is a parameter, which is a factor when we are dissolving a solute. What is that factor? That is the effect of temperature. We will look at effect of temperature in solubility. In what? In solubility. So there can be only two cases. The first case is when we have a solution which is endothermic. How does this happen? For example, what is A? If I take A, what is A? Solvent or solute?
Solvent.
Solvent. We have been taking A and denoting A as solvent. So the two solvent molecules AA will be having an intermolecular force of IMF of solvents.
So we are not
And if I
able
take,
to see the board.
sorry,
We are not able to see what you are writing.
your need
We can see.
We can see.
So I cannot see.
not then use some proper pronouns. You said we. Now BB is IMF. Just wait for a second, or you can rejoin, and that would solve
Yes.
it, I guess. IMF of solute. Okay, intermolecular forces of solute. So what happens in solvent and solute? When there was no solute in solvent, we had just AA interactions, and in solute we had BB interactions. Now in solution, what happens in solution? In solution, we have AB IMF, IMF of solute solvent, correct? The intermolecular force of attraction, which is binding the solute in the solvent. Now, if AB, this force of attraction is greater than AA, and it should be greater than BB also, then what would happen? Then I would say this is the first case that can happen. No? This is the first case that will happen. Now, what is happening? When we are dissolving the solute in solvent, these AA bonds are breaking and they are forming much greater force of attractive. These bonds are more force of attraction. Hence, what we are doing, we are putting in some minimum amount of energy. Now, this is forming new attraction. Now, AA, it breaks, gives AA. And what happens? BB, it breaks and it gives BB. Okay. Now what happens? A plus B. Now they dissolve and form AB. So here what has happened? Here what is happening? Here it is exothermic. It is endothermic. Now bonds are breaking. We have to give energy. Give energy. And here what is happening? Release energy. Right. Here the AB bond is forming and there is a release of energy. Now you will tell me if this bond AB has higher energy, release, has higher force of attraction, then what would happen? Then the whole phenomena of dissolving would be what? It will be exothermic. That means it will give out heat when we dissolve it, and delta H of solution will be what? Greater than 0 or less than 0?
Greater than.
It would be less than 0, no? when less than 0. You said it right first time, less than 0. It would be less than 0. Okay. Now, what will be the effect of temperature here? Now, the effect of temperature will be on increasing temperature. On increasing temperature. Increasing temperature, what happens? Solubility decreases. Solubility decreases. So this was the first case. Now, we write it here. Now, second case would be of AB is less than the intermolecular force of attraction of solute and solvent is less than that of AA or BB. Okay, AA or BB. Then what will happen here? This process will be endothermic. Like you can remember, for example, in the glucose, we have to stir it. So when we are stirring it, we are giving it kinetic energy. And as we are giving it kinetic energy, we are giving some kind of energy that is translated into heat energy. Then only the glucose is dissolved. Similarly for sugar also, right? So endothermic reaction. Now what will be the effect of temperature on increasing temperature? On increasing temperature, solubility increases. Solubility increases. So there are two cases. Either it can be exothermic or endothermic. And if it is endothermic, delta H of solution would be what, Amalya? Delta H of solution.
Yes, sir.
Yes, Amalya. The delta H of solution, when the process was exothermic, it was less than 0. Now, the delta H of solution will be less than 0 or greater than 0?
Greater than 0.
Greater than 0. Okay, we have been joined by someone named Einstein. I'm not letting him in. If it is Einstein, he does not need any chemistry classes. Okay. Now, endothermic. Now, there is someone who is by the name of Einstein. He's in waiting room, he or she, whoever it is. Or should I admit that? Delta H of solution is greater than 0. Now, this tell us what, that the solution needs some energy to put in, like in glucose, to make it soluble. Now, there can be some effect of pressure also. Effect of pressure. But in solid, what happens? Solids and liquids, both of them, solids and liquids, are incompressible. Hence they don't show much effect. When pressure is increased or decreased. Is changed, I should say. Pressure is changed. Effect of pressure. Now, the gases will have some effect of pressure, and also if we have liquids only, then they can show some, because here solids is present, and solids are majorly incompressible. Liquids are somewhat compressible, but not too much. When the solution has solid and liquid, it is incompressible. Hence, they don't show much effect when pressure is changed. So the major effect is of what? The major effect is of temperature. You can write this down, and if you have any doubt, let me know. Done?
No, sir.
No.
Okay.
Done, sir.
Done. Mariam, others, Fatima, done?
Yes, sir. Done.
Okay. I can copy this.
Sir.
Yes.
So after endothermic, you wrote delta H of.
Solution.
Okay, sir.
Done?
Yes, sir.
So can I move on, everyone?
Yes, sir.
Okay, fine. Now we have solubility of a gas in liquid. Solubility of gas in liquids. Solubility of gas in liquid. Now, Mariam, you must know that if you have I would say a container filled with water, and you leave it overnight, okay? And you also have put a lid on it, okay? You have put a lid on it. Now, if you leave this overnight and then open it, if you leave this overnight and open it, make the same colors and you open it, you will still have water in it. You will still have water in it. Now, if you see the lid, here, it will also contain some droplets of water, correct, everyone?
Yes, sir.
Yes, sir.
Okay, that means, it means that there is some kind of equilibrium going on here. What kind of equilibrium? H2O, which is in liquid state, it is in some kind of equilibrium. Some is evaporating and H2 in gas phase. Okay, so this is the equilibrium that is happening. Now, if there is some gas H2O, if there is some gas H2O, there is some gas H2, then here there would be some pressure due to the gas, right? There would
Sir.
be some pressure. Now this pressure is known as vapor pressure. It's known as vapor pressure. Okay, this is known as vapor pressure. I've just told you this because what happens if we have a gaseous solution? If we have gaseous solution, and remember gaseous solution, I mean, the best example would be oxygen dissolved in sea water, because if oxygen is not dissolved, then aquatic animals will not have any life, right? So gases can be dissolved in water. I'm just erasing this. You have to just keep this in mind about vapor pressure. Okay. Now, when gases are dissolved in water, what happens? Dissolved in water or any kind of liquid, what happens is, for example, you have, this is water. Let me give some water here. Okay. Let me increase this volume here. Okay. And you have some, these are some molecules of gas that is dissolved in water. Now, what do you think? Whose escaping tendency is larger? The escaping tendency of H2O molecules, that is liquid, or escaping tendency of gases, which can escape much easily from this solution?
Yes.
The gases.
Gas.
Gases.
Mm.
So I can write that escaping tendency of gas is greater than that of liquid. The next question that I'm asking is, so the vapor pressure that is here, I would say not now vapor pressure, because it's not vapor, it is particularly gas pressure, the pressure of gas here. If I measure the pressure of gas here, it will be majorly due to what? It will be majorly due to the molecules of liquid or molecules of gas. The pressure in this lid, molecules of gas, correct? Molecules of gas. So this pressure here is molecule of gas. Now, if I put some pressure here, if I apply some external pressure, what will happen? If I apply some external pressure, the gaseous molecule will be forced, they will be forced to get inside this liquid solution, right? They will be forced to get inside the liquid solution. And what will happen next? What I can say is that the concentration of gas will increase on increasing pressure. Hence, I can say that pressure is directly proportional to, now the concentration term that has been taken here is what? It is mole fraction. It is what? Mole fraction. So pressure is directly proportional to mole fraction, and then we can imply that pressure is equal to some constant. This constant is known as Kh, which is Henry's constant, multiplied by mole fraction. Now, what is this? Henry's constant. Henry's constant. The Henry's constant, the statement of Henry's constant states that Henry's law is Henry's constant, and this is Henry's law. It says what we have just observed. It says that the partial pressure of gas in vapor phase, right? This is the partial pressure of gas in vapor phase, the partial pressure of what? Of the gas in vapor phase. Gas in vapor phase. Gas in vapor phase is directly proportional to what? Directly proportional to
Fraction of the gas.
mole fraction of gas in the solution. Directly proportional to mole fraction of as solution. Okay, so I can write this chi as what? Chi b. Why chi b? Chi b because b denotes what? B denotes the mole fraction of solution. Okay, now in exam also you can write chi b, but you have to define that b chi b is what? Mole fraction of solute, that is gas. Solute, that is gas. Now, the next thing is this kh, that is Henry's constant. It depends on the nature of gas. For example, if I take nitrogen and oxygen, these two will be having different Henry's constant. Okay, these two will have different Henry's constant. The next statement about Henry's constant is that Henry's constant is what? Is dependent on the nature of solute, that is gas. That is gas here. Okay, so this was about the solubility of gas and liquid. Now, Fatima, you tell me, what would you think about the effect of temperature? If we increase the temperature, what will happen to the solubility of gas and liquid? Fatima is here. Fatima Fida. Yes.
Yes, sir. Decreases.
What will be the effect? Okay, if you unmute it so fast, I cannot hear it. I did not get it.
Decreases.
You can also write in decreases. You are saying, I guess you are saying decreases, right? That is correct. It decreases. Can somebody tell me why?
So
Why does it decrease, Ahmed?
because in like if the temperature is high, then the intermolecular, this like in gas it gets disturbed and they move faster, and in cold thing they do not move faster and they find equilibrium at that space.
Yes, that is correct. If the effect of temperature is what? On increasing the temperature, what happens? Solubility of gas decreases. Now, solubility of gas in liquid decreases, I should write. In liquid decreases as the escaping tendency of what? As the escaping tendency of gas increases on increasing temperature. Increases on increasing temperature. Okay, now you can note this down first, then the next slide. Now you should write this in a box. Okay, this is important. The partial pressure of gas in vapor phase is directly proportional to the mole fraction of gas in solution. Okay, start writing. Let me know when you are done.
Sir,
Yes.
So the value of Henry's constant is different in different medium.
Different in
Different
medium.
like different solutions.
Different solvent. I guess you mean different solvent, right?
Yeah.
It is different.
So will they give us the value of Henry's constant?
Yes, always they will. Either they will see. Here you have three variables: the pressure, the mole fraction, and the Henry's constant. They can give you the pressure and mole fraction and ask you to find Henry's constant. But if they are asking pressure or mole fraction, they have to give you Henry's constant. Okay. Two
Yes,
types
sir.
will always be given. Now they will not exactly tell you the mole fraction. They will tell you that this much of gas is dissolved in this much of liquid. Then you have to find out the mole fraction and carry on with the problem. Let me know when you are done.
Yes, sir.
Okay. Others, Mariam.
Sir, 1 minute.
Okay.
Done, sir.
Done. Okay, fine. Sanya will let me know if you are done.
Yes, sir, done.
Okay. Now copy this small part, effect of temperature. Since you are writing this, let me write a question. Question is KH of N2 at KH of N2 at 293 Kelvin is 76.48. Now you will let me know about the unit of Henry's constant. Okay. Yes, Ahmed, are you saying something?
So 67 or 76?
76. What I have written? 76. Sorry, not 67. 76. 76.48. Okay. And you can use the chat box and tell me what will be the unit of Henry's constant. Okay. At 293 Kelvin is this much. How many millimoles of nitrogen can be dissolved? Okay. Yes, correct, Ahmed. And please send your answers to Salim Raza. Millimoles of N2 can be dissolved in 1 liter of water.
So I sent to Salim Raza only.
Yes, that is right. Your answer is right. I have said your answer is right. I'm reminding others.
Okay, sir.
if N2 exerts partial pressure, of how much? Of 0.987 bar.
So what is that? How many?
Okay, this is not mini, it is millimoles. Really sorry for that. It is millimoles. Millimoles of N2 can be dissolved in 1 liter of water if N2 exerts partial pressure of, Mariam is saying, no, not right, Mariam. Partial pressure of 0.987 bar. Okay, fine. Now, others, please, Amalia, Fatma, please send your answers. What do you think? What would be the unit of Henry's constant? Okay, since, okay, fine. Just, can I have Fatima, please?
Yes, sir.
Now, tell me the Henry's law, the equation of Henry's law. What is the equation of Henry's law?
P inversely, no, P is equal to
P is equal to
Henry's constant
H
into
chi
mole fraction of solute.
mole fraction volume. Now, uh, Amalia, you will tell me. Can you tell me a unit of pressure? What is the unit of pressure?
Yes, sir.
Yes, Amalia. Pressure, unit of pressure. What is the pressure unit? Any unit of pressure?
Pascal.
Okay, Pascal. You like physics, I guess. Now, we don't know about KH, so I will write just KH. Now, uh, Mariam, you tell me about the unit of mole fraction.
There is no unit.
There is no unit. So what is the unit of Henry's constant?
Pascal per Kelvin.
Pascal. I mean, any KH has the unit. It has the unit of pressure, right? Because it will have either ATM or bar
Yeah, yeah.
or Pascal, etc. Okay, just remember this. So here, when you are given the partial pressure in bar, the KH will also be given in bar. Now you can calculate. First of all, you will apply the directly. When you see partial pressure, when you see nitrogen, it is dissolved in water that is liquid. You will apply the Henry's formula, that is pressure is equal to KH into mole fraction. Correct?
Yes, sir.
Yeah, right. Now from this, you have the partial pressure, you have the Henry's constant. You can easily find out the mole fraction. Okay, whatever it is. Then from mole fraction, you have to find the number of moles or millimoles. Number of moles or millimoles. Okay, I mean, this is the same thing, moles and millimoles. It is the difference of 10 to the power minus 3 only. Like we have gram and milligram, nothing else. Millimoles. Okay. You can give me the answer if you have calculated. Give me the answer in your chat. First, tell me how much is the mole fraction. 0.42.
Yes, sir.
That is not right.
So we have to find number of moles, right?
First of all, let me know what is the mole fraction that you have got.
Mole fraction only 0.42.
No, that is not right. What did you do? I guess you messed it up in the. This will be what?
So what is the given mass of N2?
It is bar. It is bar. Okay, fine. Yeah, it's correct. This is bar. 0.987 bar. It's fine then. Somebody wants to join again. Still, I guess. Wait a second. I have what 0.987, which is divided by what? It is divided by 76.48. Sania, can you do the division once again? It is not that much. It will be what chi b will be equal to the pressure upon Henry's constant. This will be equal to how much? The pressure is 0.987,
0.9.
right? And it is 76.48. This is also bar, then that is also bar. I'm erasing this, okay? Others, did you not get the answer?
Yes, I got it.
Send me the answer in chat, the mole fraction answer. This is also bar, this is also bar. So these two will cancel each other out. What is the answer that you will be getting? Correct. 0. Yes, Ahmed, that is correct. Amalya, Fatima, Mariam's. Amalya, I guess you can you please reconsider your answer? Just check what is the digit after 2. What is the digit after 2, and then round off again. You will get different answers. Same for Sania also. You have written 0.012, but after 2 there would be 9, I guess. Correct?
9. Yeah, it will be 0.013.
Yeah, correct. 0.013. Mariam,
Yes, sir.
did you get the answer?
Sir, I
Mole
got
fraction.
disconnected. My phone switched off. I just came.
So you didn't see the question?
No, I
But
was
you-
writing and then my phone switched off.
Yes, okay, fine. Start doing it. I mean, it has been done for you, I guess. Now, the next thing that we have to do is we have to find the mole fraction. Now, here you need to use your mind a bit. I mean, in the sense, not chemistry in general, but some general logic. That is, we have chi b is equal to what? It's equal to number of moles of B divided by number of moles of A plus number of moles of B. Now, what is number of moles of A? It is nothing but number of moles of water. Number of moles of H2O. Now, how to find the number of moles of H2O? We don't know number of moles of H2O, hence I will write here. Number of moles of H2O is equal to mass of H2O upon molar mass of H2O.
1000 by 18.
Yes, correct.
That
Not
will be
only
55.55.
55.555. 55 more, sorry. 55.55 moles. Okay. Now I'm just changing the slide here. Okay. I have got chi b is equal to number of moles of B divided by number of moles of B divided by 55.55 plus number of moles of B, plus number of moles of B. Now, we know what is chi B. We know chi B is 0.013. That is equal to NB upon 55.55 plus NB. Now, how to solve this? Just see, I can write 0.013 as 13 by 1000, correct? 13 by 1000. This is equal to NB upon 55.55 plus NB. Now, since you can see that numerator is very low, right? I mean, if NB is 13, then 55.55 plus NB will be equal to 1000, correct? Now, since you can see the ratio here, NB should be very smaller than NB should be smaller than 55.55. Hence, when we are adding these two, I can ignore this term, correct? When we are adding these two, I can ignore the NB and I will directly write, it's negligible. So I will write 13 by 1000 is equal to NB upon 55.55. 55.55. Okay. Otherwise, what you have to do, this will become quadratic equation. This will be becoming quadratic equation. Then you have to do some calculations, some major calculations. Now your answer will be somewhat less accurate, but you will reach the answer easily. Now calculate this NB. You have only linear equation in one variable. NB will be equal to 5.55 into 13 divided by 1000. What is the answer? Anyone got the answer?
Is it 0.7?
22.
That is equal to 0.722.
0.722.
Correct. Moles, 0.722 moles. Okay. Fatima, did you get the answer? I mean, I guess.
Yes, sir.
Okay, you got the answer, no? So if I want to convert this into millimoles, what I have to do?
Multiply with 10 raised to 3.
Yes, multiply with 10 raised to 3. So this will be equal to 722 millimoles. 722 millimoles. Okay. Now done. So I can I move to the next slide?
Yes, sir.
Okay, fine.
Yes, sir.
Now applications of Henry's law. What are some major applications of Henry's law? Applications of Henry's law. So the first application is when you have CO2 dissolved in soda. CO2 is dissolved in soda, right? So when it is dissolved in soda, it is sealed under very high pressure. Why? Because if we give much pressure, then what will happen? The concentration of more and more CO2 we can put in, and we can dissolve more and more CO2 in the soda water. So to increase the, what we have to do, to increase the solubility. What? To increase the solubility. Increase the solubility of what? Solubility of CO2. Of CO2 where? In soda water, or I can say in soda. In soda, the bottle is packed at high pressure, right? At high pressure. So when we increase the pressure, what happens? The solubility increases. We are using the Henry's law, and then that is why what happens? The CO2, more and more CO2 is dissolved in the soda water. Now, second thing, Now, what do you think if we go on higher altitudes? If I go on higher altitude, what happens? The pressure increases or decreases?
Increases.
Pressure increases. Okay, fine. Let me check that. This is sea level. This is sea level. So what will be the pressure here?
Low.
Low. Yes, anyone can, does anyone, the numeric term, the number, the quantity, what will be the pressure at sea level?
Don't know.
0.
Zero.
1 bar.
Yes, correct. 1 bar or 1 atm. That is why we see 1 atmospheric pressure, right? The pressure is what? Pressure is 1 atm. Okay, the pressure is 1 atm. Okay. Now, who is applying this pressure, by the way? Who is applying this pressure?
The air.
The air is applying the pressure. Why is air applying pressure? Because it is attracted by gravity. The molecules, the air molecule. Why do we have atmosphere in Earth? Because the Earth has high gravitational constant. It has high gravity. So the molecules of air are attracted, and if they are attracted, they are applying a pressure on. They're applying a pressure on our heads. So that is 180. That is equal to 180. Now, if I go to some, let me increase this. Okay. Now, if I go to some hill, now, if I go to some hill, what do you think?
Pressure.
Am I having more pressure here? I am experiencing more atmosphere in sea level, or am I experiencing more atmosphere in the mountains?
The mountain.
The mountain.
Really? I am not experiencing this much of pressure in mountain. See, this much of atmosphere is not there in mountain because I'm in high altitude. If I'm in high altitude, what happens? I am not
Pressure is
experiencing.
more, right?
No, it is not more. How it will be more? I mean, like if you think about it, this is not a trick question. Okay, just disclaimer: this is not a trick question. See, the only thing that is applying pressure is the atmosphere, right? And as I go up and up, what happens? The atmosphere is decreasing for us, na? So if the whole atmosphere is decreasing, the volume of atmosphere that is experienced by our body is decreasing as we go up, right? So what will happen? The pressure will decrease, na?
Yes, sir.
Yes, sir.
Does anyone has any? I mean, maybe you must be. It must be stuck in your head. If you go up, the pressure increases. But now, if you logically think, can you recorrect it, or do you have any doubt here?
No, sir.
No, sir.
No doubt.
Mariam?
Yes, sir.
Okay. So if we go up, what happens at high altitudes?
The pressure decreases.
At high altitudes, the pressure decreases. Now, our body is generally accustomed to what? To experience one atmospheric pressure. It is accustomed to experience one atmospheric pressure, and our body has the whole biological system in which we now one atmospheric pressure. What does it do? At one atmospheric pressure, the amount of oxygen that is dissolved in our blood would be some quantity, but if we decrease the pressure, that quantity of oxygen, the concentration of oxygen will also decrease. At high altitude, the pressure decreases. As a consequence, the concentration, or I can say the solubility of oxygen, now solubility of oxygen in our body as well as the solubility of oxygen in the air, right? The partial pressure of oxygen now in the ground level will be less than that in altitude. The solubility of oxygen is also decreased. Hence, what happens? Hence, what happened? Our body and our blood does not get
Enough of oxygen.
enough of oxygen. Yes, that is the right sentence. Hence, body and blood don't receive enough of oxygen. This leads to a disease called anoxia. This leads to a disease called anoxia, or what? Or we have what is it? So it is called altitude sickness. Yes, altitude sickness. Altitude sickness. Okay. Write this down. Pressure is less than 1 atm.
So we have to draw.
It's your choice. Let me know when you're done. Done.
Yes, sir. Done.
No, sir.
Okay. Done.
Yes, sir.
And third application. Have you heard of scuba divers?
Yes, sir.
Yes.
Divers, है ना? They go inside. So when they go inside, how do they breathe?
Oxygen.
Oxygen.
Oxygen
They have the
tank.
cylinder.
Cylinder,
Okay.
yeah.
Oxygen cylinder. Just oxygen.
Tank with diluted helium.
Diluted helium. Okay. That means, what do you mean by diluted helium? There is a solution of helium in which there is helium and what? Some other gas?
Helium, nitrogen, and oxygen.
Helium, nitrogen, and oxygen. Okay, fine. That is correct, because see, when we breathe, what do we intake, I mean, all the gases are nitrogen is, we also taking nitrogen, oxygen, and other gases, right? So some nitrogen is also consumed by our body, and some oxygen is also consumed by our body. Okay. So both nitrogen and oxygen are essential. The other gases, that is CO2 and some other minute gases, these are not essential. So we have helium or any noble gas. Argon also is taken sometimes. Helium, then nitrogen, and oxygen. Okay. So in this helium, this is the inert. Okay, it is inert. It doesn't cause anything. It does not cause anything. I guess there are some, if you inhale helium with your mouth and you speak, you sound funny, right?
Yes, sir.
Yes,
Huh?
sir.
So
Never
you have
tried.
seen those videos.
Yes, sir.
Never
So
tried.
by that, what can you conclude? You can conclude that helium is not harmful for us.
Yes.
So helium is inert. Helium is not harmful for us. Nitrogen, in other case, nitrogen at some higher concentration, it is toxic. It is toxic at high concentration. Toxic at, and our body does not, it cannot accumulate nitrogen very easily. It cannot accumulate. That is why it becomes toxic at high concentration. Okay, what happens here? That I will tell. At high concentration. Now, oxygen, our oxygen, if you give us, I mean, too much of oxygen is very bad. But if I have like 78% of nitrogen and somewhat 21% oxygen and 1% helium, correct? Now this makes us 100%. So this is somewhat the nitrogen and oxygen concentration in atmosphere, the same kind of what I have given in the tank also. Now oxygen is not toxic, so I will not write anything in oxygen. What happens when we go inside? The pressure increases or decreases?
Increases.
As we go inside water, pressure increases. Pressure increases. Now, if pressure will increase, solubility of
Gases will increase.
solubility of gases will increase. Now, if the solubility of gases increases, then nitrogen, oxygen, and helium all will be dissolved in a higher quantity than atmospheric pressure. But as the scuba diver is going up, now they are going back to the bank. As divers go back to sea level, solubility starts to decrease. Now, what do I mean? If it will start to decrease, or EAC, wait a second, I'm just writing here, down arrow, starts to decrease. Now, what will happen if it will start to decrease? Nitrogen and oxygen. Nitrogen will be in the blood because oxygen is accumulated and it has been taken out. Nitrogen will be in blood as nitrogen, and if nitrogen is first dissolved, now N2 is dissolved in our blood. Now the pressure decreases, P decreases. What will happen? N2 will go out. Right? This is blood. Now N2 has exited the blood. Now, if N2 has exited the blood, if a gas is present in a liquid, what happens? What do you see?
Bubbles.
Now you can do what? You can bubbles. You can shake a water bottle and you will see bubbles, right? Why does that happen? Because some air molecules get inside it. The gases molecule get inside water. It will form bubble. This bubbles, this N2 gas which is in bubble, it is harmful and it leads to disease. Which is called bends. Bends is the name of disease. Okay. Now, what is the solution to this? The solution to this is, if we decrease the concentration of nitrogen in tank, then if the availability of nitrogen will decrease, obviously the solubility will decrease. Correct?
Yes,
Yes.
sir.
You agree? So this is the solution. The solution is what? In tanks of scuba divers, the composition of gases. Ahmed, can you please turn off your mic? 11.7% is helium and 56.2% is nitrogen. 2%, and we have 1% of oxygen. Okay, 32.1% oxygen. To avoid, this is to avoid the disease, Bent's concentration of nitrogen is decreased. Is decreased. Okay, you can now write this down.
Sir,
Mhm.
we have to learn the percentage.
Yes, learn it. 3% is only now. Composition of gases in diverse tank. Diverse tank. Done?
Yes, sir.
Sanya?
Yes, sir, done.
Okay, now write this. Done? Now,
No,
meanwhile, you
sir.
write. Done? No, not done?
No,
No,
sir.
sir.
Okay, that's fine. Meanwhile, you write. Let me write a question of Henry's law only. If 0.2524 grams of gas is dissolved in 1 liter of water, 1 liter of water at 1.5 atm pressure, 1.5 atm pressure, how much of gas will dissolve if the pressure is just what, raised to, let us increase, raised to 60 atm, 6.0 atm at constant temperature, at constant temperature, constant temperature. We have 1 atm, 6 atm, yes. This is constant temperature. Should I give you some hint how to do it?
No, sir.
Yes, sir.
No, sir.
Yes, sir. Okay, fine. First of all, we have been given 0.25 grams of dissolve. Okay, fine. So initially there is some quantity of gas which is dissolved in 1 liter of water, and the pressure is 1 atm. The pressure is 1 atm. So I can write pressure 1. The first case is 1.5 atm. Sorry, not 1 atm. It is 1.5 atm. And the solubility and the how much is dissolved, mass dissolved, is equal to. Now I can write solubility. I can write solubility is equal to 0.25, 0.24 grams, 0.24 grams, okay, or 0.24 grams upon 0.24 plus 55. I mean, not 0.24, but rather number of moles of, I can write the chi b if I want to write. Chi b will be equal to nb upon nb plus what? N plus number of moles of H2O, right? Number of moles of H2O. Now this will be NB1, this will be solubility 1. Now pressure 2 is equal to 6 atm, 6.0 atm. Okay, 6.0 atm. But the thing that is constant between the P1 and there will be this B1, it is now this will be chi B2, will be some amount. Now in both the terms, KH is constant, right? So P1
Yes, sir.
chi 1 is equal to P2 chi 2,
Right.
which is equal to Henry's constant.
Henry's
Correct?
constant.
So here you have been given in 2.4 grams. So you can directly write, you can use 0.24 grams also. Okay, because it is the solubility, not exactly you have been given mole fraction. You have been given, now this is a term of concentration. Now this is, you can write this as solubility. The initial statement was that the solubility is directly proportional to, and in general, we usually take mole fraction. But since you have been given grams, exactly, this is the solubility 0.24 grams in 1 liter, then you can use solubility as S. Okay, you can use S, solubility per liter. Done? Did you get the answer?
Sir, the amount of this NB is same, right?
No, you don't have to take exactly. See, the statement of Henry's law was the solubility will increase if we increase the pressure. So here what you have to do was the solubility was how much? Solubility is what? Solubility is nothing but concentration. No? Solubility is what? It's concentration. So here what you have to do, here you have to write the S1 is equal to 0.24 grams per liter of water, 0.24 grams per liter of water, since you have not been given what is this gas which is dissolved, right? So if the gas was given, then you would have calculated what? You would have calculated the molar mass, right? Molar mass and then the number of moles. So solubility is S1. S2 you have to find out is equal to how much? How much grams in liters? The statement is solubility of gas is directly proportional to mole fraction. The sky here I have written it means solubility. It's so I can write what? Pressure is equal to KH. P1 is equal to KH S1. Similarly, P2 is equal to KH S2. Right. I mean, are you okay with the idea that I can write solubility? I mean, it is just solubility. So I can represent solubility in terms of concentration. I can write mole fraction also. I can write solubility also. Are you okay with this idea? Are you okay with this concept?
Yes, sir.
Hannah? The statement says solubility. Usually we do it in mole fraction, but if mole fraction is not there, then we can directly write solubility. So KH is equal to P1S1, which is equal to P2S2. Now what is P1? P1 is given as 1.5 atm. Solubility is given as 0.24 grams, I guess 0.24 grams, which is equal to, I have to find the P2 is given as 6 atm. I have to find S2. So S2 will be equal to 1.5 into 0.24. This is atm and gram divided by 6 atm. So yeah, I can remove the atms. Now I will get the solubility in, sorry, this is gram liter inverse. This is also gram liter inverse. Yes, how much?
0.6.
Wait a second. 1.5, 0.25 grams. Okay. Let me check. Others, did you get the answer?
Yes, 0.6.
0.6.
Yeah. Gram.
Yes, sir.
Gram liter inverse.
0.6 or something else? 0.6 exactly?
Yes, sir.
0.06. No,
Correct.
0.06.
0.06. P1S1 is equal to P2S2. This is pressure. This is the solubility at that point. This is 6 atm. This is the solubility at. There is something happening here. Now, don't you think this is grams per liter? It is. Don't you think something messy happened here? Something different happened here? What do you think? Is this statement correct?
Sir, the unit of the constant is wrong also.
The unit of constant is wrong.
Yeah. I don't know.
So what happened here? You all went with the flow. You all went with the flow now. So one thing, the first thing that you should see that when we had 1.5 atm, we had 0.24. Now when the pressure is increased, the solubility has decreased. How? Tell me, is this statement correct?
Yes,
No.
sir. Maybe.
That's maybe. Nice.
No.
Maybe. Okay.
No, sir.
No, na. Yeah, okay, fine. Who pointed out? Sanya pointed out. What will be the correct equation?
P1 by S1.
Yes, correct. Okay. Just keep in mind, okay, don't be sleepy. KH is equal to how much? KH is equal to P1 upon S1,
Yes,
right? And this KH is equal to P2 upon S2.
S2.
Now do again. So what will be the equation from these two? I can write P1 upon S1 is equal to P2 upon S2. Write it again.
Sir, 0.78.
No, I don't think so. I can write this as, what is the pressure one? Pressure one is 1.5 atm. And the solubility is what? S1 is what? How much?
37.5.
0.24 grams. Wait a second. Let me. Now this is P2 is 6 atm upon S2. So S2 will be equal to 6 atm upon 1.5 into 0.24.
Sir, 24 will go up, right?
Oh yes, sorry. Sorry, yes, correct. 0.24 will go up. So how much will be this much?
0.78.
No, do it again. It
No,
is
no, no,
1.5.
no, no. So it is 108 something. Like I multiplied into 3, 24 into 3.
6.0. Sorry. 6.0 into 0.24.
10.
Now you tell me 1.5. Now 1.5 into 6. How many times?
98, 98, 98, sir.
98 again. No, not 98. Now tell me.
0.98.
0.98. Yes.
Yeah.
4 times.
No.
0.
Tell me this. Okay, fine. Ahmed, please be with me. Tell me this, Ahmed. Okay. 1.5 and which is divided by 6. How much will be this
4.
one?
4.
4. Now
4
tell
into
me
0.24 will be
4 into
0.996.
0.96 grams per liter. Grams per liters. Okay.
Yes,
4
sir.
4 is 16, na? How you are telling
Yes,
0.98? 0.96. 0.96. Okay, now let us just get a slight taste of what? Slight taste of solubility of liquid in liquids. Okay, solubility of liquids and liquids. Now I'm just giving you a bit of what I can say, a broad picture. You have liquid as solvent. You have liquid as solvent. Liquid as solvent. Now what happens? You can give the solute. You can dissolve. You can dissolve gases. You can dissolve liquids. And you can also dissolve solids. Okay. So when we have seen about gases, right? When we dissolve gas, what happens? Henry's law.
yes, sir.
Yes, Henry's law. That means the partial pressure is directly proportional to solubility. Now, generally we write solubility as what? We in NCERT and your syllabus you have been told that when you see solubility, it has been expressed as solubility has been expressed as what? Mole fraction. Chi that is mole fraction, and here KH is equal to what? Henry's constant, and P is the partial pressure of gas but where? In vapor phase. Okay. Now what is chi b? That is the Mole fraction.
Mole fraction.
Mole fraction of what?
Solute.
Of gas. Now this is gas, solute or gas in solution. Okay, in solution. Now when we have liquids, you have Raoult's law. The law is called Raoult's law. Okay, I mean, you don't have to worry so much about the Raoult's law. The name itself, that is Raults, Raoult's law. Raoult's law. Now, what do you think? If I ask you the pressure, it will be directly proportional to. See, it will be directly proportional to what? We have liquid here. So the escaping tendency of liquid, that is, if I tell this as A and this as B, right? These all are B because this is solute. Same kind of escaping tendency because both are liquids. Somewhat will be very much not very difference in higher and greater, higher and lower, but the difference will be very minute. So the escaping tendency will be dependent on. It will be dependent on the mole fraction of A, also the mole fraction of and mole fraction of B. That means both A and B will be present in the vapor phase, correct? Right?
Yes, sir.
No? What do you
Yes,
think?
sir.
And the pressure will depend on both the mole fraction of chi and chi. Okay. Now let us imagine. this. I have this container, and in which I start with the mole fraction chi A is equal to 1. So what will be chi B? Tell me.
0.
Yes, very good. If I have chi, now here, if I have chi A is equal to 0, what will be chi B?
B1.
1. So now here we have pure A. Here we have pure B. Right? Pure A and pure B. Now, if the escaping tendency, and here I have pressure, here I have the vapor pressure. Okay, I'm writing here vapor pressure. So if I have pure A, this is vapor pressure. If I have pure A, and let us take just some magnitude here. This is the vapor pressure of pure A. This is the vapor pressure of pure A. If I have pure B, the vapor pressure is this much. The vapor pressure is this much. So what do you think? Vapor pressure of A is less than vapor pressure of B, correct?
Yes, sir.
Yes,
Now, if
sir.
I will dissolve it, in water, if I will dissolve it, A and B both are in water. Now, what do you think? What will be more? In the vapor phase? Whose the escaping tendency of B is greater or A is greater? Escaping
B.
tendency B is greater.
B.
So more, So more of B will be present.
Yes, sir.
That should also show in our this equation that we are going to write for Raoult's law. The equation that we are going to Raoult's law. Now let us imagine. I want to see what is the pressure. The pressure is directly proportional to chi B. Obviously, it is directly proportional to chi A or chi B. Now, when it is pure, it will be directly proportional to chi A. Now, the pressure will be equal to some constant.
Yes, sir.
Into chi A. Correct?
Yes, sir.
Yes or no? Yes. Okay, fine. Now, if I want to find what is this constant, what is the mole fraction of pure A? 1. So I will write this constant is equal to the pressure of, or vapor pressure of
A.
pure A. Am I right?
Yes, sir.
Yes,
And
sir.
similarly, right? So this equation, I can say that this equation is PA for PA. For PB, the equation will be what? Constant into
Chi B.
chi B, right? So I can write this constant. This is also a pressure. So I will write this constant as P naught of A. I will write this as P naught of A. Let me just put that naught above and A in the subscript, P naught of A. So I can call this as what? P naught of B. Now, the equation for Raoult's law will be what? Equation for Raoult's law will be the vapor pressure of solution. Vapor pressure of solution is equal to the partial pressure due to A plus the partial pressure due to B. Now, as we have seen that P of A is equal to what? P naught of A chi A Pb is equal to what? P naught of B into chi B. This is what? This is our Rod's law. This is our Rod's law. Got it?
Yes, sir.
Right. Now, what do you think about this case? If we have solid, the pressure will be directly proportional to what?
Temperature.
Temperature. I am asking about the solubility. I mean, the amount of solid which is present in the solvent. What do you think? If I start to add more and more solid, what do you think? Will the vapor pressure increase or decrease?
Decrease.
Why it will decrease? See,
So it
first of
will
all, we had what?
increase.
Increase, decrease. I mean, if somebody asks why, the answer changes. Now we have just
No,
water
sir,
here.
I can reason it.
You can reason it. You said what? Increase or decrease?
I said increase now.
Pressure will increase, vapor pressure. Okay, fine. Now reason it out. How?
Okay, sir. Like when it was not in solution, that time it would not like it would not have any vapor. But when we add that to any liquid, then it will start vaporizing because it is in a liquid solution now.
Fine. Okay, fine. Did anyone get what was the reason? I could not get it
No,
properly.
sir.
Okay, can you please rephrase it, reformulate your argument? Ahmed, no? Okay. Listen, in pure liquid, what is there? We have only liquid. So escaping tendency of liquid is greater than solid. I can say that, right? Escaping tendency of liquid is greater than that of solid. Any issue with this statement? Anyone?
No, sir.
No. Now here we have only liquid. Here we have liquid plus solid. So obviously the vapor pressure will decrease, na?
Yes, sir.
Right? So vapor pressure, it decreases in the liquid and solid solution. So if I want to write what is the, this is, let me say this is P1, this is P2. Okay. So if I want to write the difference in, the pressure, so I will write P2 minus P1, minus initial is equal to delta P. Now what is delta P? Delta P will be equal to P naught of 1, because in pure liquid, we have only liquid. So I am writing P naught of, I should write A, that is solvent. P naught of A, that is solvent, right? Minus P1, that is minus P1. No, not P1. I should write P2. P2. Okay. Now this one I can write. Wait a second. Sorry. This one I can write pure liquid, and that is pressure. Okay, fine. Now I can write pure liquid, and this will be equal to P naught of A minus P2 can be written as what? Tell me.
P1 plus P naught.
P1 plus P naught. No, in terms of chi2, I want, here we have chi1, that is chi of A, and here also we have chi of B. Okay, so what do you think? I can say P2. What do you think? The vapor mole fraction and solvent. What do you think?
Plus chi B.
P2 will be directly proportional to the amount of
Chi A.
A, right?
Yes, sir.
Chi A, right? So I can say that this P2 will be also equal to P naught of A and chi A. Now I can write this as P naught of A 1 minus chi B. Correct? Can I write this?
Yes, sir.
Right? So again, I can write this is minus. Now P2 will be what? P naught of A minus, this will be minus chi B. Sorry, I should write it like this, 1 minus chi B. 1 minus chi b. 1 minus chi b. Now, let me rearrange all these things. All these things, let me rearrange. We have now in the pure liquid minus the solution, the pressure of solution, which is equal to P naught. Okay, sorry, this is P naught 1. This is also equal to P naught of 1 minus P naught 1 and chi 1. Now this was equal to how much? P naught of 1. You can write 1 minus chi 1. Sorry, 1 minus chi 2. 1 minus chi 2 or chi 1. 1 minus chi 1, sorry. P1 is taken here and 1 minus chi 1. This will be equal to P naught 1 and this will be equal to chi 2. So this is delta P. This is the delta P. Now the change in pressure is directly proportional to the decrease in vapor pressure is directly proportional to mole fraction of solute. Okay. Now this is a bit far away now. This is a bit far away. This solids, the vapor pressure when solid liquid is present, it is in relative lowering of RLVP, relative lowering of vapor pressure in colligative properties. Now, after today's class, we will learn about Raoult's law and we will solve some questions on Raoult's law. Okay. So if you want, you can write this down. And you can just write this directly proportional to chi of P. Delta P is directly proportional to chi of P here. This is the big picture of this chapter if we deal with solubility. Henry's law, Raoult's law, then relative lowering of vapor pressure, that is delta P is directly proportional to chi B. You can note this down. Whether you don't have any doubts in the assignments, right?
No, sir.
No, sir.
Sir,
Just tell me.
an assignment, wait, in the new assignment, that is molarity and
Molality, okay, fine.
question number 2 and question number 4 is a bit confusing.
That's a bit confusing. Let me see it. Question number 2. Calculate the number of moles of methanol in 5 liters of its 2 molal solution if the density of solution is 0.981 kg. Okay. If everyone has written this, can I take a new slide?
Yes, sir.
Okay. So Amalia, just be with me. Tell me what are the things that you have been given?
Volume.
Volume of
Of methanol. If I'm not wrong.
volume of solvent or solution?
Solute.
See, calculate the number of moles of methanol. Okay, calculate the number of moles of methanol in 5 liter of 2 molar solution. So they have given the volume and the concentration of the solution. 5 liter of 2 molar. Right. So volume of solution is how much? They have given what? 5 liter.
5 liter of
solution. And they have given the solution concentration is 2 molar. This is small, so this will be molar. Okay. Now, this is volume of solution is equal to 5 liter. Volume of solution is equal to 5 liter. If the density, calculate the number of moles of methanol and 5 liter, if they have been given here. Now, you have to change from molarity to first molality, then you can convert 2 molar solution. That means 2 moles, 2 molar solution in 5 liter of solution. So we have molality is molarity. This is molality is equal to how much? The formula is number of moles upon
Yes, sir.
number of, what is the formula for molality?
Molality is a number of solute.
Hmm.
No, number of solvent.
Molality again, number of moles of, है ना?
Yes, sir.
Not number of moles of solute upon what?
Mass. No, volume of a solution.
No, mass of solvent in kg. Mass of solvent in kg. Now you have been given this. You have been given what? This is molal is equal to 2m. 2 molar. This is equal to 2 moles per kg, and you have to find the number of moles of solute, and the mass of solvent is also not given. This is equal to moles of solute. Now mass is also not given. So how can we deal with it? I have been given that 5 liter of solution is there. If 5 liter of solution is there, this moles will be constant, right? So if I can write molarity is equal to in 1 liter. If I write in 1 liter, okay, again 2 molar solution is there, so I cannot write one. I mean, directly you can use this formula, but let us derive this formula first. Let's derive this formula. What is the formula given? It is given molar is equal to m. What is m? This is molarity upon d, that is density into mb, which is multiplied by m, which is again molarity. Okay, no, I have to check this again. It cannot be written like this. Others don't have any problem with this question?
Sir, even I had.
So
I
why
was
you are-
doing it today
Okay, and
I did not start any.
and I did not do it. I forgot to ask you. Now, when she mentioned, I remember.
when she mentioned, you remembered. Okay, fine. A solution is prepared by the calculated number of moles, and when it's around 5 liters, 2 molar solution. That is equal to this much. Density is equal to, we have number of moles is equal to volume into molarity. I have to find molarity, and molarity is what? Molarity is equal to, I mean, we can do one thing which is quite dicey to do. This density is equal to mass by volume. So mass, I don't have density, I have mass. I have got mass now. So density will be equal to 0.987. Volume is, this is how much? This is gram per liter. Density is what? Kg per liter. Kg liter inverse. Mass is given. I have to find mass. Volume is 5 liters. Mass would be equal to 0.987 into 5 liters. This will be equal to, and this will be in kg. This one will be equal to 0.987 into 5, which is equal to 4.935 kgs. 4.935 kg. This is the mass of solution. Mass of solution is this much. So in 4.935 kgs, we have what? We have 2 moles of, no, 2 moles. We have 2 into 5 moles of, that is 10, that is equal to 10 moles of ethanol. Correct? So 10 moles of ethanol. So mass of 10 moles of ethanol will be how much? Tell me. 1 mole of ethanol.
CH3 is 2OH.
Yes. CH3, CH2, OH. This is how much? This one is how much? 12 plus 3,
plus 3
15 plus
Sir,
14 plus.
plus 2.
they asked methanol, not ethanol.
So this is CH3OH. So how much will be this?
32.
So 33, I guess.
This will be 17 plus
16.
17 plus
15, huh?
15.
So
How much? Carbon 12, hydrogen 3.
Okay, yes, so 32.
So this
Yes.
one will be 32. 32 grams. This is for grams per mole. We have how many? 10 moles. So mass of 10 moles is equal to how much? 32 grams into 10 is equal to 320 grams. 320 grams. Okay. What did we have to find? I guess we found it. We had to find the calculate the number of moles of methanol in 5 liter of its and this will be no, wait a second. This is 5.93 kg, 5 liter. I'm messing it up somewhere. Again, this is solvent. Again, this is solvent. Wait a second. I have to consider. I cannot write into 5 here. I cannot write into 5 here. Because this is 4.35 in kgs. Correct, that is correct. So number of moles is 2 molal. Okay, 2 moles in 1 kg of 2 moles in 1 kg of water. 2 moles in 1 kg of water. That means in 4935 kg, we have water also here, no? We have water also, and we have ethanol also. So in 1 kg of water, there is 2 moles. Okay, fine. In 1 kg of water, there is 2 moles. This is the solution. If I do directly with density, then I can get probably. If I do directly with density, but that would not be correct. Just wait a second. Let me solve it if I take my density. I can get a relationship, but wait a second. We have been given molality. The mole fraction is needed. If I have molarity and molality, then I guess I will need some mole fraction because Na will be coming. Can I get back to you for this question
Yes.
next on Sunday? I'll
Yes,
get back
sir.
to you. Okay.
Thank you, sir.
Fourth is the same question on what? Solution of peroxide is etna by mass. What is the molarity of solution? This is, I guess we have done this type of question, Amalia. Fourth number. No. Fourth number.
Yes, sir.
You have been given percentage mass, right? From here you will find out mass of in 100 gram mass of solute. Now the percentage mass is given how much? 15.22 grams. So this mass of solute, wait a second, this 15.2 percentage. So in 100 grams, this will be 15.2 grams of solute, and solution will be, mass of solution is 100 grams. Now this is what? Hydrogen peroxide. Hydrogen peroxide is H2O2. So molar mass of H2O2 is 216 to the 32 plus 2, that is 34 grams per mole. Correct? Right?
Yes, sir.
Yes, sir.
Now, if I want to find the volume, then I can write volume is equal to, we have the density now. Density is equal to mass upon volume. Volume will be equal to mass upon
Density.
So the mass is given as
Mass is 15.2.
No, mass of solution. You have to find the
100.
volume of solution.
Yes,
100 grams.
100.
Density is given as how much? 1.01 grams milliliter per milliliter. No, so milliliter will be here. So what will be the volume? 1 divided by 100 divided by 1.99. 99.0999 is there, so I can write 99.1 ml. Correct?
Yes, sir.
So now this is easy. Right, you have got ml, you have got that is 34 grams, so you will find number of moles of H2O2, which will be equal to 15.2 grams upon 34 grams per mole. Right, then you can find out, you will have moles here, you will convert this into liters, then divide it. Okay.
Yes, sir.
Yes, sir.
And we have been doing something else. No.
Sir.
3.2 grams per mass. Yes, take it. Fine.
Sir, can I submit the assignment without writing the second question?
You can.
Okay.
Thank you, sir.
Okay, welcome. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.